Okay, never mind. Great. Yeah, so thank you everybody for joining. My name is Itay. I'm giving this talk on behalf of the MicroBooNE collaboration, and I'm going to concentrate mainly on applying sparse CNNs in MicroBooNE. This talk is going to have a little bit of overlap with what Francois and Jeremy presented. And as I assume that except for this session, most people here in the recording or that actually attend live are not from neutrino physics. I'm going to give a brief introduction to the MicroBooNE detector and to what are we exactly looking at. So the microbooster neutrino experiment is a 85-ton liquid argon time projection chamber located at the boosted neutrino beam at Fermilab. The beam itself is it's a spectrum, but it peaks at about 1 GeV neutrino muon beam. And the experiment is an appearance experiment, which means we are producing neutrino muons, but we are trying to measure electron neutrinos. So that means we're actually looking for lepton flavor distinguishing. So we want to distinguish whether our end products are including muons or electrons. We are operating since 2015, and as this is a surface detector, we suffer from about the 5 kilohertz of cosmics. Give or take the sizes of the detector is written here on the right image. It's about 10.4 times 2.5 times 2.3 meters. So the motivation for this experiment is that the MicroBooNE experiment sees a 4.5 sigma mu E-like low energy axis, as you can see on the plot on the right. However, you do need new physics to explain that. This does not sit good in a 3 neutrino model, not also in a global fit for a 3+1 neutrino model. And one of the problems with MicroBooNE is that they have limited capability to distinguish electron versus gammas. MicroBooNE is a Cherenkov light detector, so if there's a shower, they cannot distinguish whether it is coming from one electron or maybe from a decay of a pi naught, which produce 2 gammas, which are close to one to another. And as you can see, the red histogram is the biggest background, and that's a pi naught misidentification. So MicroBooNE is actually sitting on the same beam that MicroBooNE is sitting at about the same baseline, very similar baseline. However, it incorporates a LAR TPC technology instead of a Cherenkov light detector. So briefly, just how the detector works. So when a neutrino interacts with the detector medium, in our case, the liquid argon, it produces a prompt scintillation, which we measure by an array of PMTs. And any charged particle produced in that interaction or scattered by that interaction, when it travels through the media, it produces ionization electrons, which are then drifted by the external electric field applied to the anode plane, which consists of 3 wire planes, 2 induction plane, and 1 collection plane. The wire pitch is about 3 millimeters. And thus, for each interaction, we get 3 images, which this is an example for an interaction. So the U and V plane are the induction plane, and the Y plane is the collection plane. Just a brief to understand how to look at these images. So the Y-axis is the time, and the X-axis is the wire. So essentially, each vertical line is a waveform. If you stack all of them together, you get this image. And this is the image for the same type, it's the same interaction exactly, but with different orientation according to the wire orientations. So this is an example for a 1 electron, 1 proton, very nice interaction. So yeah, as you already probably saw in Francois' talk, this slide, I'm going to go through this briefly. The nice advantages we can have with the LAR TPC is that you can clearly see there's a distinct topology difference between the muon, which you can see on the bottom left in the orange ellipse, which is just a track crossing, no branches almost at all. It's just a straight line, and a shower, which is in the center of this image. And this one, you can see there's a lot of topology that you can look at. There are a lot of branches and breaches, gaps in between. So that's the first thing we can get. And then the second thing is if we actually zoom into the interaction point, we can distinguish between gammas or gammas coming from a decay of a pi naught and electrons. And the way to do that is to check whether there's a gap from the vertex. So if there's no gap, it means the electron was actually produced into interaction. And if there is a gap, it means that in the interaction point, there was either a gamma or a pi naught, which then decayed to a gamma and then produced a shower. So these are the big two advantages we have for LRTPC. And just to focus on what exactly are we looking at. So if we look at the plot here on the right, this is the cross-section, the dominant cross-section for neutrino interactions. And the blue area here is the energy regime in which MicroBooNE sees the excess. So you see this regime is dominant by quasi-elastic interaction. And this means actually there's a neutrino coming in, a lepton coming out, and a proton. So we're actually looking for an interaction of this type, specifically saying 1 lepton, 1 proton, 0 pions. And then we have 2 types of data sets. One which is our expected signal, which is a 1E, 1P, and this is the same example as I showed before. This is what we're looking for. And then the second sample we collect is the 1mu, 1P, and that's for constraining the flux and the systematics. So you can see a 1mu, 1P has 2 distinct showers, which you can distinguish, two clear showers, which you can distinguish between using the QDX. Right, so those are the samples we are collecting. You can see that the morphology of them is quite simple. Most of them have a V-like shape at some plane, has a V-like shape, and so they are very easy. They're supposed to be much easier to pick up. If we look at our analysis chain in MicroBooNE, so there are several analyses looking for the same thing. I'm focusing on the deep learning low energy analysis chain, and as you can see, as Francois already described, we're not taking the entire image and spitting in it, plugging it into a neural net and spitting out what type of interaction was it. There are many levels to this interaction, and I'm going to focus about the pixel classifier, which we use the Sparse SSNet. So a word about semantic segmentation that we are doing in pixel level. So you can see on the right image, this is just an example. What you want to do in semantic segmentation is just input an image, and then you want to say that you want the network to predict for each pixel from which type of class it's coming. So for example, in MicroBooNE case, we would like to say whether this is a track-like or a shower-like, and you can see that on the images on the bottom right. So the input image is just the ADC counts or the waveforms, and the output from the network is the prediction for each pixel. And as you can see, the yellow pixels are the track-likes, and the blue cyan or light blue pixels are shower-like. And this has been proved to work in MicroBooNE using convolutional neural nets, but for track shower only classification, and using the dense algebra, the standard dense algebra techniques. For that, we had to crop our image to about 60 or 60 something images because of GPU memory limitation. And so the reason this is working that good is that in the close vicinity of an event, the data is dense and is important. However, the occupancy of important pixels in MicroBooNE within our threshold is about 0.5%. So that means we're losing a lot by taking all the data. So performing the dense multiplication is very non-optimal because we are doing many multiplication of non-important pixels, which takes more time. And moreover, we have to save those non-important pixels, which takes more memory. In addition, if you apply convolutional layer to sparse data, you create the blurring effect of the sparse data. So for example, if you look at the image on the left, this is the input image, for example, the digit 0. After several convolution layer, it becomes blurred, more blurred and more blurred just because of the way convolution works. And this means we are actually decreasing the spatial precision of our images. Recently, a Facebook AI research group have developed what they call the Submanifold sparse convolutional neural net. This is specifically good for optimized for sparse data. And as I said, in LRTPC, the data is sparse, so less than 1% of the pixels are non-zero. And if we take in MicroBooNE specifically, the percentage of pixels which are within our threshold, that's even a factor 2 lower, so a 0.5%. And this algorithm is optimized for 3D. And if you want to have more detail, to hear more details about 3D reconstruction, you can see Francois' talk, which were 2 talks just before me. I think the main focus in that is in his talk and not in his poster. And as I said, it's a submanifold. So the idea is that whenever the data lies in an effective lower dimensionality than the image itself, so this works. And for example, in our case, a track is a 1-dimensional entity embedded in a 2-dimensional image. So the general idea in a nutshell is that prior training, we define a mask to select only the important pixels. So an example could be pixels with pixel value above 0. So there's an energy deposition there. And that moves us from saving a value per pixel, the height times the width, to actually save just a row, column, and value times the number of pixels which are important. So this reduces dramatically the time and space resources. And in addition, we allow only pixels which are activated in the input layer to become activated in a dense layer or in the output layer, and this prevents the blurring. So an example here, if we would have applied on each of these images a kernel of size 3 on regular dense CNN algebra, all of the red pixels would become activated. However, because of this constraint, only the green pixels become activated. So you can see even in deeper layer and in hidden layers, the sparsity of the data is preserved. Now, a work done by our group, mainly Domain and Terao, have proved that on available large CPC data, this has shown a big improvement, both in accuracy, computational time, and memory usage. And this is an improvement which is a game changer. So we have decided to incorporate that in MicroBooNE. And the data sample that we used in order to train our network consists of particles generated and propagated in the detector, including all the detector response. So for example, dead wires, recombination, diffusion effects, etc. And we produce 2 types of particles. One which is a particle bomb, and that's just producing some multiplicity of electron, gammas, muon, charged pions, and protons. And that's to mimic the interaction itself. And then we throw in random numbers of muons, and that's just to mimic cosmic ray, to make the image a little bit dirtier or a little bit harder to distinguish. The labeling is done by a single hot labels. So i.e. that means for each pixel, there's only one label that it can get. And the labels are a heavy ionized particle, that's mainly protons, minimum ionizing particle, which are muons and pions, showers, delta rays, and Michel electrons. And we do give priority to the labeling. And that's important mainly for downstream analysis. So for example, for vertexing. And the priority is given exactly by the order I read the classes. We've produced a training sample of about 120,000 events with a test sample about 23.5 events. The mask we use to remove is done to remove noise while keeping important info. So our threshold is about ADC counts above 10 and below 300. And this corresponds, this is the 0.5% pixels I was talking about. And finally, we treat each plane on its own. So they're distinct weights per plane. There is no information shared between the planes at the moment. The network we are using is again, is a hybrid between UNet and ResNet, which we call the UResNet. This was demonstrated, as I said, using standard dense algebra in MicroBooNE. The idea of this network is that it has an encoder and a decoder. The encoder takes the data, learns features from various special resolution, and then the decoder part upsamples the different features and creates the high special resolution image of the prediction. So for example, in this case, on the left, you can see the ADC. This is the input for the image. And on the right, you can see the predictions. And of course, This layer has skip connections between each layer from the encoder to the decoder part to help assist the reconstructing the image, and it uses a residual skip lines within each block. So in addition, in order to prevent class statistics imbalance, we apply a pixel weighting. So if you saw Francois' talk, you saw that about, I think, 30 to 40% of our, or maybe it was 20 to 30% of our pixels are coming from either a track or a shower. So that means for other particles, this is very low. So to prevent from the network to focus on those big chunks of pixels, and to make sure that the loss function is not governed by those clusters, we apply a pixel weighting. Unlike the original paper where they applied a class weighting, we apply a pixel-wise weighting. And we apply two types of pixel-wise weighting. We apply a cluster weighting, which is more similar to what they used as a cluster weighting, which means we apply for each pixel a weight which is proportional to the inverse of its size. And this you can see if you look these examples. So the images here are events from the test sample toy Monte Carlo, which I produced. This is the input image, is the labels, and the output image. Well, it's not an output, but the image on the right is the weights assigned for each pixel. So you can see there's a small cluster of hip here, which gets orange colors, and orange, if you see in the color bar, these are higher weights comparing to these magenta or purplish pixels. So that's one type of weighting. And then the other is what we call a vertex weighting. That means wherever there's a pixel from one class, within a 3 pixel distance to a different class, we apply a weight to it, which is the highest weight we apply. And you can see that if you look on the image on the right, you can see that where the shower gets near the track, it gets a higher and higher weighting. Also in the vertex itself, I don't know if it's fully visible. You can see there's a yellow color which becomes orangey on the hip and becomes more purplish when it becomes to the shower. So, and the reason for that one is that obviously, if we have a track and in the center of the track there is one misidentified pixel, it's very easy to remove that one in downstream analysis. And moreover, it's very hard for the network to confuse there. However, where there are pixels from various classes, one near another, it's very hard to the network to distinguish these. And we want to make sure the network actually focuses on those pixels. So going into the results, the images on the right are just a zoomed in version of the image on the left. And the image on the left, you can see the loss and accuracy with and without the weighting we applied on the training sample. And you can see the accuracy also on the test sample. Now, the red dot is the configuration we actually chose, which was the optimal configuration before starting to overtrain the network. The total accuracy we get on the training is about 97%, and on the inference is about 95%. And this is actually going to be improved, as I will show in a sec. Total training time went down to about 8 hours, with an average inference time done on a CPU without optimizing the network. Is about 2 seconds per image without cropping the image itself. So we're taking the full image at once. Memory consumption went down to about 1 gigabyte per image. Again, full image. So looking at the confusion matrix, this is an example of the Y plane. So this is the collection plane. We can see, and this is normalized to truth. So each column sums to 1. We can see that obviously the highest probabilities are on the diagonal as expected. The biggest misidentifications are Delta and Michelle's, which are identified as showers, which is also anticipated as they have quite similar morphologies. Other planes show quite the same numbers. They're in the backup slide if you're interested to see the differences between them. Now, in the MicroBooNE analysis at the moment, we're not taking all the 5 labels. We're just looking at 2 classes, which is track and shower, and that's because we're looking for a 1E, 1P, or a 1U, 1P. So we want to know a track and a shower. If we renormalize the percentage I've shown before, renormalize them to define a track to be a hip and a MIP and a shower to be all the rest, we see that the total accuracy is about 99%. And the purity is about the same with these numbers, which is quite impressive. Let's have a look how this actually looks like on our Toy Monte Carlo test sample. So this is an example of an image on the top left. This is the input image. This is the ADC counts. On the top right is the label. Of course, this is not used on the test sample when trying to define the accuracy, but it is produced, and it's nice to see, for us to see whether the predictions are nice or not. On the bottom left are the weights assigned for each pixel. Again, this is not used for the inference, it is used for the training. And on the bottom right is the predictions from the image. And you can see this image is predicted quite nice. I think most of the pixels here are predicted correctly, except for this small chunk here, which is a Michel electron, which is a delta and is predicted as a shower. This actually can be solved by post-processing, as the prediction class is just taking to be now the argmax of the probabilities. So this can be improved by taking a higher threshold. Let's say delta is defined just as a delta if the delta score is above 50% or above 0.5. However, this is happening so seldomly that we have not looked into improving that at the moment. Another nice example, this is a more complicated one. Again, the same scheme, and you can see the image is predicting quite well. Two things which you can see here. One, there's a misidentification, which is actually a bigger misidentification. It's a shower, which is misidentified as a MIP. And then the second thing, which is nice to see, is that the priority we're giving is actually preserved. So you can see when the track crosses the shower, the pixels are labeled as a track. However, when the track crosses the hip, the pixels are labeled as a hip. So those are for simple Monte Carlo, which I produced. These are the training and test sample. Let's see how it looks like when we're looking about a full neutrino interaction simulation. Now, the nice thing about these sparse SSNet is that we are actually training our sample on a 500 by 12 by 500 by 12 Monte Carlo sample. And we use this exact same weights to predict a full BNB simulation, which is 1008 by 3456. And the way we are doing our simulation currently is we simulate the interaction, propagate the particles, etc. And then in order to simulate the cosmics, we have found out that it is actually better to take off-beam data, which consists only of cosmics, normalize it for the exposure, and randomly plug it into on top of the simulation interaction. This is what we call an overlay. And then we can see the network prediction on that. So an example of an event like that, and one comment here is most people, I assume, are coming from actually collider physics, which you guys have the benefit of actually knowing at least the axis where the interaction happened. This is not our case. So this is the input image. This image is actually simple to recognize, simple-ish to recognize if I ask where the interaction is, which is exactly here. This is a nice example of a 1 electron, 1 proton interaction. And again, I will zoom in a sec. So these are the images, as I said, the interaction simulation, the overlay, and then the prediction of the network. And if we zoom in on the important part, we can see the network is predicting quite well the 1E, 1P. This is our signal-like events. Looking at a more complicated event, this event is a bit harder to recognize where the interaction actually happens. If you're watching this in a recording, you can pause and try to find it. If not, I'm moving on. So the interaction is actually here. This is an example of a 1 mu, 1p interaction. And again, this is the scheme. If I zoom in, now it's clear to see where the interaction actually happens. So this performs quite well on the full BNB simulation that we have. So to summarize, MicroBooNE data can be represented by 2D images. And one of the first tasks in our analysis and deep learning analysis is the semantic segmentation. As the data is very sparse, as I said, it's less than 1% non-zero pixel and less than 0.5% within our threshold. It's obvious to use the sparse SSNet, or it's demanding to use the sparse SSNet. And some of the improvements, you can see that instead of cropping our image into 60 images, and we did the 60 just because the GPU memory limitation had us do 60, we now do not need to crop the image at all. So only this is a factor 60 improvement in time. And that's before taking the improvement in the time that actually the network is faster. There's a big improvement in the memory usage. It's about 1 GB per full image. The improvement in the time, it's about 2 seconds per full image done on a CPU. This allows to better utilize the existing infrastructure. So there's no need to skew the network to make sure it fits a CPU. And it has a higher accuracy as we prevent the blurring of the data. And again, as I said, this is scalable to 3D and to bigger detectors. And if you want more details about that, again, you can see Francois's talk, one of his talks about 3-dimensional reconstruction chains. With that, I will finish, and if you guys have questions.
Great, thank you. Are there questions? Dave, your hand is up, but I think it was up from before.
Oh, I think I forgot to lower. But I actually did have a question. So when you're sparsifying your image, going way back to the beginning,
right?
Do you have any overlap regions between those images?
Let me go back to, I think this is where I explained. What do you mean overlap?
So these images are all distinct, or are there any? So I'm wondering how you connect them together. Is that just implicit in the way you've ordered them inside the data?
Right. So let's look at an image. Let's look at this, for example. So as I said, on these images, each image is treated on its plane is treated on its own. So we actually we are training 3 different neural nets, and we have distinct weights per plane. There's no share of information between planes.
Mm-hmm.
Right. Now within a plane, each pixel, well, this is a 2D image, so each pixel, there's no ambiguity, right? Each pixel has a specific row and column, and that's the only data we save on it, the row, column, and the value, right?
Yeah, I mean, going back to that circle image where you divided it up into several local images.
But so those are just an example to show when you perform the convolution, mm-hmm. then you don't allow the red images to become activated. So you only allow the green images.
I see.
So this is just, a heuristic way to show this.
Okay.
That's the only reason for this. So instead of having, this image, so you should think about that as the input image is on the left, and then this is hidden layer and another hidden layer, et cetera, sure. Right? And here, even in hidden layers, the image looks exactly the same. Well, I mean, right? It doesn't get blurred. That's the idea. But again, as I said, this is just a heuristic way to show it.
Anyone else have questions? I guess I had one. I think I know the answer, but just to cross-check. You talked about adding detector effects and such. Have you found your networks to be particularly sensitive to any of those? I'm assuming not because of the sparsity, but I'm just curious.
Not really. Not really. I have not seen so the accuracy is so high that it's really hard to fixate where failures happen, right? So for the labeling itself at this point, there's almost no, right? There's almost no effect of that.
Okay. Okay, thank you. Okay.